Hello everyone, welcome to the Reading Club, and in today's episode we are going to discuss this paper, which is Structure Driven Fix and Propagate Heuristics for Mixed Integer Programming. It was published in MPC in 2019. It was by Gamrath, Gerald and others. Okay, so let's start with discussing what fix and propagate heuristic is, and then we will talk about the structure driven part. Okay, so what is fix and propagate? So we have our standard mixed integer programming, right? So we have minimizing cx ax less than equal to b, and x is between some bounds, right? This bounds could be infinity also. Okay, now what we want to do is that we want to take one variable, let's say x1, and fix this variable to some value, let's say v1. Okay, this is just a guess. I don't know whether my actually x1 will take this value v1 in any feasible solution, but I'm just guessing. Okay, so let's say I just fixed it. Then this will imply some bound changes and other things on other variables, right? So we have a bunch of constraints over here, right? So ax is less than equal to b and x is also between some bounds. These are all constraints. So this constraint can imply some bounds on other variables. It might say that because x1 is fixed to v1, now x2, whatever it was its previous bounds were, it's now between, let's say, 3 and 5, right? So previously those bounds could be 10 and 0. So if I just reduce the bounds from 0 to increase the lower bound from 0 to 3 and reduce the upper bound from 10 to 5 just by fixing x1 to v1. It might even happen that some other variable, let's say x3, right, just because I fixed x1 to this value v1, it got fixed to say a value 4, right? And these are all sorts of changes that we can expect, right? So this is our fixing part, right? So this is fix, and all of these bound changes that are implied because of this fix, we are going to derive it using propagate, right? So this is fix and propagate framework, and we don't just simply stop here, right? So we fix one variable and then we propagate the bound changes, and then we continue doing that, right? So we are not going to fix all the variables just by propagating, right? So we still have, like, even this x2 itself is not really fixed yet, so we don't know the solution yet, right? So what we want to do is we want to do this in a loop. So fix, propagate, and keep doing this for a while. Okay, so now I will, after doing this, I have some reduced bounds. So let's say after this I am going to fix some other variable, let's say x5 to some value 5, and then do more propagate, and so on and so forth, right? And then again, like, I will go and fix some other variable, and then it will also lead to some more propagation, and we keep doing this. What will happen is that eventually there are two outcomes, right? So one is that I can't really, so I have fixed a lot of variables, and I know I no longer have any other variables to left to fix. So two things can happen. One is that in this process, when I'm propagating, right, some variables bounds domain, basically this domain part becomes completely empty, right? So that variable cannot take any values anymore, right? So that's a bad thing. Why? Because that means that this is infeasible, right? So which basically means that one of these guesses or more of these guesses are wrong, right? So x1 might not be v1, or x5 now might not be v5, and so on and so forth, right? So those guesses that I made are wrong, and I end up getting infeasibility. The other thing that can happen, which we are actually interested in, is we can hit a solution, right? So this is an integer feasible solution that we just found by doing this kind of fixing and propagating, and that's what we want to do, right? So we want to find this kind of solutions before even we start solving the first linear program, the root node linear program. So that's the goal of this heuristic. Now, there are a lot of questions in this heuristic, right? So how do we fix the variables, right? So how did I decide whether to fix x1 first or x5 first, or even when I fix x1 to then like which value to fix to, right? All those questions are there, and this is like a general framework, right? and we are going to answer these questions and use structural information that is present in our machine learning program to drive this process of fixing and propagating, right? So let's talk about let's actually reiterate the entire framework again. So we are going to fix a variable, then we are going to propagate, and we will keep doing this for a while, right? And two things can happen, right? So one is that I can hit infeasibility. In this case, I can even like backtrack one level and unfix my last variable and then refix it to some other value and see if I can like get rid of this infeasibility. Or the other thing that can happen is I can find a solution right away by fixing all the variables to their corresponding values, right? So we are only fixing integer variables, right? So it might happen that I basically fixed all the integer variables or most of those integer variables, and then I might need to solve a linear program after that, right? So this is a little bit expensive compared to this, but if I have fixed all the integer variables, then this a linear program is kind of not that expensive to solve compared to solving a linear program where nothing is fixed, right? And in some cases, I might not fix all the integer variables, so I might solve an LP and then I round some variables, right? I might have to round those integer variables to the nearest integer values and see if I can find a solution just like that, right? So like if I have found the solution, I don't have to do anything, but if I haven't found a solution, and if I don't no longer have confidence about which variables to fix and everything, then I can just simply jump to this LP solving and rounding procedure, right? And even after that, if things are not everything is fixed or infeasibility is not reached, in that case, these people also solved LNS. So what is this large neighborhood search? LNS is basically like I have a bunch of variables, right? And most of these variables are fixed to some values, but there is a small portion of these variables that are not fixed, right? So what they do is they basically solve a small MIP for this, like you can even call it submip. Okay, so this submip will basically find the best values for this remaining variables, and that's how you complete your solution. So this is even more expensive, right? So what we want to do is we want to fix as many variables as we can in this part, and if we have fixed enough number of variables, then we will try out this one and this one, right? So this we will try out these two things only if we have fixed enough number of variables. If we haven't fixed enough number of variables, then we will abort. Okay, so this is the entire framework of fix and propagate heuristics, and now we'll see how to use structure information to guide this fix and propagate part. Okay, so the first structure that we are going to talk about is Clique table. Clique table. Okay, so what is Clique table? So let's say we have this kind of a constraint where we have x1 plus x2 plus x3 plus up to some more variables, let's say up to x10, right? And this is less than or equal to 1, and all of this are binary variables. Okay, so x belongs to 0, 1, right? So in this case, this is called a Clique type of a constraint. Okay, it's a very specific constraint. So what do I mean by this is that all of these variables, all 10 variables, are connected to each other in the sense that if any one of this variable is fixed to value 1, then all the other variables are fixed to value 0, right? So it's a standard type of constraint. So this is called one click. Okay, and this kind of constraints might be directly present in our mixed integer programming, like so we have this kind of a constraint set, right? So one or more of these constraints are directly taking of this type of a form, or it might happen that we can detect this type of clicks. Okay, so when we do some pre-processing or probing and all those things, then we might find that this set of variables, right, all this set of variables, take only one of them can take value 1. If one of them takes the value 1, then all the others are taking value 0. So that means they are all in a clique, and so we can put this into a table, right? So this is a special structure that is that all lot of MIP solvers use. It's called Clique table. So they basically store all these Clique tables, right? So they store that these 10 variables are part of one clique, and then this detected clique that we found is also another clique in the table, and then they basically have a list of those cliques. Okay, so this is one clique, this is second clique, this is third clique, this is fourth clique, this is fifth clique. Some cliques might be bigger, some cliques might be smaller, and so on and so forth, right? So how can we use this clique table information for guiding our fix and propagate, right? So we had our fix then propagate, right? So what these people do is that they pick variables which are part of larger cliques, right? So when I have to fix one variable, then I have a lot of choices, right? I have 10 here, and a lot of variables are here in this entire MIP, right? So which one to pick? Pick the one which appears in a largest clique, right? So in this case, like this is my largest clique. Then why do I pick the largest clique? Because if I fix only one of them, that means it will propagate the bounds to all the other variables. In this case, like if I fix say x2 to 1, then x1 to x10 except x2, all of those are fixed to 0. That means I have fixed, by fixing one, I automatically propagated a value to the other 9 variables, right? So that's the goal. I want to propagate as much as possible. Okay, so let's say I picked up this clique, which is the largest, the 10 variable clique. Then still I have to pick which one of those 10 variables to fix. And basically, like, you can pick anything, but they even went further and they said, like, pick the clique for which is like the cheapest variable to fix, right? So which has the objective value Cj is smallest. We have our objective here, right? Minima is Cx. So for whichever variable the objective is smallest, that is the cheapest, just fix that. So it will likely result in it basically means that it is easier to fix. That means it is more unlikely that we will hit infeasibility while doing this fix and propagate, right? So infeasibility is a bad result for us. We want to avoid it as much as possible. So fix the one which has small Cj, small objective coefficient, out of the one largest clique that we picked. If we have multiple cliques of same size, we can pick it randomly. Same way, like if we have in the largest clique, if we have multiple variables which have same objective coefficient, and pick randomly, right? So that's using clique table to guide this fix and propagate, and this actually is kind of helpful. Like, we, instead of picking variables randomly for fixing, if we do it this way, then it is more helpful and it results in more solutions, right? So this is not the best approach. Like, this is not the one that results in maximum number of solutions, but the solutions are also of high quality, right? In the sense that these are not garbage solutions which are easy to find. They are like giving me a decent objective value, these solutions, right? If I found it this way. So that's Clique, and then we'll see the next structure. Okay, so now we are going to talk about the next structure, which is called variable bound graph. Okay, so this is a graph that is stored, and we are talking about variable bounds. So typically when I talk about bounds, right, so it is a fixed bound, right? So when we have a x, right, so it is less than equal to 5 and greater equal to say 3. So 3 and 5 are fixed values. So this is fixed bounds. But in our constraints, we can have things like this, right? So x plus 2y is say less than equal to 3, right? So this is now a variable bound for x, right? So this implies a bound on x in other way by by a bound on y, right? So x is less than equal to 3 minus 2y. So a lower bound on y basically implies an upper bound on x, right? So we can basically put this relation over here, right? So lower bound on y, right? This implies upper bound on x, right? Similarly, then there are more things that can do, right? So this also goes other way around, right? So here we can also say that the lower bound on x, right, this implies an upper bound on y, right? And this these are basically like I'm basically trying to draw a graph over here, right? So these are my nodes, right, and these are my edges, and this can be like connected to other things, right? So this can imply upper bound on x could mean like some constraint from some other constraint, right? So this is one constraint, it implies two of this kind of things. There might be more constraints that I have. It might, let's say, upper bound on say z, right? We have z, and then we have here this one also might imply an upper bound on z, and so on and so forth. This can basically make a complete graph based on this kind of relations, right? So these are called variable bounds, and we are constructing this variable bound graph, right? So we have this complete graph like this, and again, like this constraint might be directly present, or you can actually deduce them by some other pre-processing or branching or whatever you are doing, right? So may not be directly present in our constraint set, so we can detect them. Okay, so we can just simply put whenever we detect those kind of relations in this graph, and this graph can help us guide our fix and propagate, right? So this graph can actually even have cycles, right? So this, and so on and so forth. But yeah, what we want to do is we want to first remove these cycles and convert this into a directed acyclic graph, right? So if I have a cycle like this, I will randomly remove one of those edges, let's say, right? So now this is a directed acyclic graph, and on directed acyclic graph, if you know a little bit of graph theory, then you can do topological sort, right? So it's an ordering of these vertices. This is 1, this is 2, so it's okay, not 1. So this is, let's say, 1, this is 2, and this is 3, this is 4, it's 5. In this sense, like if there is an edge in my graph, then in this ordering, the basically this is the tail and this is the head of the edge. So the head part, this part, will always come after the tail in my ordering. Okay, so that's called the topological sort. And what's the point of doing this is that if I pick the first node which is not yet processed, right, and if I try to fix this bound, then it will imply more changes deeper into the graph, right? So that's the idea behind it. So I will do this topological sort, and then I will pick the one that is the first one that is not yet processed, right? So that's the key idea, but there are few bunch of variants that they consider for doing this fix and propagate heuristic, right? So first one is that although this in this case, like my first node is lower bound on x, I might want to consider fixing an upper bound, right? So fix means there are two parts: picking a variable which is x, and then a bound which bound to pick, right? So in the Clique constraints, we are going to always fix the variables to 1, right? So that's why it will imply all the other variables to 0. But here we have a choice. We can also fix it to an upper bound, right? So this is something that they discuss, that even though this might be lower bound, you can actually fix it to upper bound. There are reasons behind why that might be helpful, and they experimentally evaluate all those things. And you can also consider the objective value, right? So if the objective is positive or negative, based on that you can make your decision. You can also just simply discard the objective. Don't take into account the objective, just use this information, whatever is here, right, and move forward with this. So yeah, that's how you can use a variable bound for our fix and propagate, right? So we have variable bounds, and that will guide which variable to fix and to probably which value. Okay, so the last structure that we are going to use is called variable locks. Right? So if I have constraints like x1 plus 3x2 minus 2x3, all of this is less than equal to say 5. So this implies locks on variables, right? So what I mean by locks is that it bounds my x1 variable on the upper side, right? So this is an up lock for x1, right, and also on x2. So I can't arbitrarily increase x1 to a certain any value. I have a bound on it. So this is one up lock, and similarly, this is one constraint is also a down lock on our variable x3. Okay, so this is up locks and down locks, and we have more constraints. So we have bunch of up locks for x1 and bunch of down locks for x1. Similarly, we have a bunch of up locks and down locks for x2, x3, and all the variables, right? So the previous structures were kind of restricted in the sense that not all variables can be part of the clique. So like if the variable is part of if the variable is not binary, then it's basically we don't really care about cliques and everything, right? So similarly, where not all variables have variable bounds, they might not be part of the entire variable bound graph, right? But this up and down locks, pretty much all variables will have, right? Because these are the constraints, and every constraint in which a variable appears, it will either impose a up lock or a down lock on that variable, or sometimes even equality constraints might be there, so it will imply both locks, up and down, both locks, right? So what do we want to do here, right? So we want to use this variable locks information for our fix and propagate heuristic. How can we do this? So first of all, we are going to compute which variable has highest or lowest number of ups and down locks, right? So we just compute the sum of locks on this, right? So if I have two, let's say x1 has 5 locks, x2 has 10 locks, x3 has 15 locks, and so on and so forth. That means that x3 is more restricted in my problem compared to x1 and x2, right? So I will pick the one, which is this one, right, as my variable that I want to fix, right? So this is like, it is more restricted. That means it will lead to more propagation, and because of this more propagation, I will likely find a feasible solution. So again, like which value to fix to is basically like whichever is more, whichever is less locks, right? So if I have more up locks than down locks, if I have more of this, then I will fix it to the lower bound. If I have more of down locks, then I will fix it to the upper bound, right? So this is how I go for fix and propagate. And compared to the other two structures, this will fix a lot of variables, right? So the other two structure might stop because I ran out of cliques, or I ran out of nodes in my variable graph to fix. So, but this one will pretty much fix everything for us. So the likelihood of us going to LP or LNS part is reduced, right? So this is in that sense, like this variable locks part produces more solutions than the other two structures. But the other two structures are, if you, I mean, they all did like a lot of evaluations and everything, lot of experiments, and they find out that these other two structures are also kind of helpful, because they are not generating as many solutions as this one, but they are generating more quality solution, right? So the solutions which have better objective. So this one is not doing that, not like matching their quality of solutions, this variable logs part, right? So that's pretty much kind of the three structures that they used. Okay, so finally I want to basically talk about the results, and so the results were pretty good. They basically evaluated their results on MIPlib, three different MIPlibs, right? So previous versions of MIPlib and Coral dataset. Like these are all very famous data sets for if you want to evaluate an effect of a new algorithm or something in MIPS, right? So they basically found a lot of good solutions, and they found those good solutions, and those good solutions basically helped reduce the overall optimality time. And typically when you want to measure the effect of a heuristic, you basically measure primal integral, and those primal integrals were also pretty much like improved to a very significant value, right? So these heuristics were very helpful, and there are structured experiments. You should basically read about that, because it gives you a key of how to actually fix the parameters, right? So they have a lot of parameters about this heuristic, and they used a lot of experiments, and they describe all those things to figure it out what should be the default values of these parameters. Okay, so that's pretty much it. Let's take a look at the summary of what we have seen, right? So this is the concept map that I prepared after reading this paper. So what did we learn? So we learned about fix and propagate heuristic, like fix and propagate framework, right? And we learned about the global structures in our mixed integer program, which is we learned about the Clique table, variable bounds graph, and variable logs. And all of this can guide the variable ordering in fix and propagate heuristics, right? And once I do this fix and propagate, if not enough variables are fixed, then I stop, but otherwise I pass whatever has been fixed to an LP. I solve the LP, and then I try to do the rounding part. If I don't have a solution still, then I go on and pass this fixing to linear to solve this large neighborhood search LNS, and yeah, after that I can't really do much. So that's the overall structure of this fix and propagate heuristics, which is guided by this global structure. And about the solution qualities, right? So the variable logs gives you more solutions, because you fix more things compared to the Clique table and variable bounds, and those two things give you a high quality solution, right? So that's pretty much all for this video. Thanks for watching, and we will add more videos in the future. Thank you.